Normally when you watch these videos, you watch them before class. The purpose of this one is to take what we've looked at in class and look at it a second time, just in case it was a little bit confusing, because there's a lot going on. So we're just going to run through organic reactions as we know them, as we've learned them, if you were there, of course, and just make sure that a couple things get touched on again. We're going to look at some mechanisms or how the reaction happens at the atomic level. Most of that is not really required, but if it helps you understand what's going on and why we end up drawing the products that we draw, then that's fantastic. So I want you to remember about organic reactions, it's the functional group. Find the functional group, figure out what kind of functional group it is, and maybe even some of the things that are possible with that, because one of the problems that people run into is they'll start saying things like, well, this reaction turns an OH into something else. There's no real magic going on, and I understand that in most cases that's just how you look at it, but it's really, really important to start finding the functional group and understanding what that functional group can do. And then oftentimes it's also the carbon of that functional group. It's going to be doing something, or it's going to be somehow involved, even if it doesn't look like it at first glance. So we'll start with alkenes, and alkenes are our first reactive group, and they can do a lot of different things. And one of the things we saw them doing was an electrophilic addition. And now addition means something is being added. And the big thing that we were adding was something across the double bond. So both carbons of the double bond get involved. And then when we're finished, both carbons have had something added to them. It's not always obvious at the beginning, but that's what's happening. I'm going to break two bonds. I'm going to break one bond on the alkene, so the double bond, one of the bonds goes, and I'm going to break the bond in the original, in the thing that's being added. So two bonds get broken, two bonds get formed. And if I look at this example here, where I've got an alkene or just the skeleton of it and a hydrogen chloride coming in, what's going to happen during the reaction is that the bond of the carbon-carbon double bond, one of the bonds, breaks, and those electrons, remember there's two electrons in that bond, they both stay with their carbon, but they move out. So instead of being shared between the two carbons, they are now going to be shared somewhere else. Similar thing is happening with the hydrogen chloride. The electrons that are shared between hydrogen and chlorine, they stop being shared between hydrogen and chlorine and they move in a different direction to pair up or share up with the electrons from that carbon-carbon double bond. And then we end up doing something like that. Now, with this one, in the skeleton model, I could have that hydrogen chloride oriented differently. And there's really no reason why one is preferred over the other, but we know that there are times of preference. So we're not going to worry too much about it here. That comes in a minute or so. But understand that HCl could be reoriented as ClH. So we'll look at a couple of addition examples, and then that idea of preference comes into it. We can add water across the double bond. Now water is not particularly reactive, so I usually have to add a catalyst, that's the H+, to give it a bit of a kickstart. The details of what's going on with that aren't particularly important. We can work it through in class if you want, but understand that because water is not all that reactive, I need to up the stakes a little bit. I can also, now the first one I should have said is that carbon-carbon double bond is right in the middle. So whether I had the water added, in this case, left to right, the OH on the left, the H on the right, or right to left, the name of that structure would be the same thing because I would number it differently. So because that's symmetric, my product is the same no matter what. But in the second example, I now have an option. I could either have the OH, the alcohol group, added to the middle carbon or the third carbon, the end carbon, which would actually be number 1 at that point. Because of the way preference works, only one of those is going to be favored. And what we find out, and this is a thing called Markovnikov's rule, and the way that some will talk about Markovnikov's rule is by looking at the hydrogens. My preference is to look at the oncoming group, the more obvious group, the group that indicates the functional group. So in this case, the OH group. That's going to go to the carbon that is attached to more carbons. In other words, in this particular example, the alcohol group on the end is not preferred, and it's not going to happen. Your job will be to predict and generally only worry about the preferred carbon. So we generally don't have to worry about what happens if, is there a small percentage of the ones that do. So we'll just kind of take the major product and move on. Certain things can have a cis-trans isomer. And what's worthwhile to notice there, or remember, is that whatever I draw on paper might not be static. It might not be fixed. So bonds can actually rotate, but they don't rotate on paper. So I can have cis-trans isomers if the actual structure is fixed. So if I look at this particular example, there I'm adding something across a double bond. It's an addition. But my final product, I can draw it as if it were sort of trans. But if I remember what I know about single bonds, there's rotation there. So it's drawn as a trans, but it could easily be drawn as a cis. In other words, there's no fixed bond there. That thing has free rotation. So cis-trans isomers are not a possibility on this one. On the other hand, in a ring, now because of the nature of the ring, I can't do this without breaking things. I can't rotate the bond. So now, however this thing starts out, however the groups are added, whether they're added on the same side or on opposite sides, that's how it's stuck. So then cis-trans isomers are possible. Ozonolysis. Ozonolysis is probably one of my favorite reactions. It's one that has a really kind of almost a crazy mechanism going on. I'm going to show you the mechanism, but we're not going to be required to know the mechanism. So in ozonolysis, what happens is, and that's the one where we've got step 1, step 2. So step 1 is O3, step 2 is zinc/water. In reality, those would be done as separate steps. Most of what we do is going to be done on paper, so it doesn't really matter for us that much. But when I add ozone in to this thing, I end up with that pretty crazy looking intermediate product. We don't need to know that though. But then what happens is I take that crazy looking intermediate product and I dump in zinc mixed with water. Now zinc will not dissolve in water, it just makes this slurry, muddy kind of stuff, kind of gray mud. I dump that in the mix. And what happens is the zinc reacts with the stuff and breaks out a couple of pieces as zinc oxide, or breaks out the one oxygen as zinc oxide, and where those bonds broke, new bonds have to form. So I end up with a carbon-oxygen double bond on both of the remaining bits. Now that reaction is probably at its best when there's a certain amount of symmetry involved. So if I have a symmetric molecule and I break that using ozonolysis, I get 2 of the same kind of thing, which would be awesome. If with something like this I end up with 3 really if I look at the other product. So I'd have to do some work to kind of get some separation going on there. That's possible. It's a little inconvenient. For us, all we really need to worry about is our overall summary. So here's my starting material, here's my reactant, reaction conditions, here's my products. Electrophilic substitution. Now substitution, of course, means that something's being replaced. So it's not just we're adding across a double bond. What we're doing is we're taking something off and putting something new on. Now again, the mechanism isn't that important, but I do want to spend a bit of time talking about it. So our basic thing was this. Now I've just picked out one of the reactants, one of the reaction conditions, one of the possibilities. And the main reason for that is this is the one that we're going to see most often. I want to caution you though, and maybe I should have used something other than the CH3Cl, the chloromethane, is that if I make that carbon bit coming in a little bit longer, so instead of a chloromethane, maybe it's a chloroethane, or on a propane or something like that, if I make that incoming carbon bit longer, I need to be really, really careful about what is being and where it's attaching to the ring. Not for the ring, but for the carbon chain. And the word of advice I can give you is look at the functional group, not just of the benzene ring, but the functional group that's on the alkyl halide. That's the carbon that's going to be reacting. Anyhow, here's how it starts. Again, we don't need to know the mechanism, but here's how it starts. We start out with the reactant mixing with and reacting with the catalyst to generate these two new things. And the carbon there is quite a reactive thing. We rarely see carbon being an ion. So when carbon is an ion, things are going to happen. Well, now that carbon, that ionic carbon, has such a strong desire for electrons, it's able to disrupt the very, very stable benzene ring. So electrons from the benzene ring come out and bond with it. If I started with an ion, I'm going to finish with an ion. So now that carbon, single incoming carbon, is happy, it's bonded up, no more an ionic charge, but now one of the carbons in the ring has that. Well, it only has so many options to get rid of that charge, and one of them is to pull electrons away from that hydrogen in that previous carbon. So that's what it does. It grabs electrons, or the electrons from the carbon-hydrogen bond are broken, and not the electrons are broken, they're pulled out of that bond, so the bond is broken, and they're pulled into a new bond between carbon and carbon, and off floats that hydrogen. Now that hydrogen ion, don't worry about it, it's going to go back and find that catalyst, that aluminum, well, it's not even aluminum chloride anymore, it's aluminum with 4 chlorines and an ionic charge. And it's going to grab one of those chlorines. And then the hydrogen ion will react with the chlorine, or the chloride ion, to make hydrogen chloride, and then you're left with aluminum chloride again. So our catalyst gets regenerated near the end. The reactions themselves, anything I'm going to give you is going to follow these patterns. You'll have to be thinking about what's changed and about preference and what happens if that carbon chain is a little bit longer. But it's all about functional groups. So we can get here if we're paying attention to the functional groups, and if we're focused on the functional groups, it's not that bad. We'll talk to you in class and we'll try a few more examples. See you then.